And this will really be where the acronyms start to make sense. And then, as we said, through the rest of the day, we'll make sure we keep using them and reusing them so they become part of your language.
All right. Thank you, Janet. Thanks, Jamie. Thanks to Mike. I guess he's already taken off for kicking us off nicely. And Mark for hosting. It's actually kind of cool to be back here. I began my career here just down the hall in 1995. So I was in computational chemistry. I was doing molecular modeling support for the antibacterial programs at the time, and literally was just down in the next wing here. So it's fun to be back. And I was thinking, as Mike, was sort of talking about the accumulation of data due to the sort of movement to the high throughput experimentation now in the process area, I realized that there was probably an event here that maybe presaged my eventual movement into IT, right, into the dark side entirely. And that when I was in graduate school, I had access to silicon graphics machines. I could find 2 or 3 around the department to get some things going in parallel. When I got here, and I had access to Crays, both here and at West Point, and massive number of processors, I could do the amount of work overnight that used to take me several weeks, which was really cool, except then it turns out that these command line scripted languages, the output wasn't really designed for data mining. So it was sort of multiple lines per each sort of thing. So oh my God, now how am I going to understand what all this actually means now? And that's actually what drove me to try and learn Perl at the time, so that I could sort of post-process all the output from Charm and actually figure out what happened and understand what was going on. So, and in some ways, right, that's a microcosm of where we frequently find ourselves these days, right, with data. We can generate an enormous amounts. We're getting really good at that, and we need to get better at how to manage that. I'm going to start off by sort of describing where the high-level problem statement that really initiated Allotrope Foundation, and what has really driven us, what's led to our mission has driven us to create what we have to date. And I want to put it in particular terms because it kind of sets up how we're addressing the problem. I think that, in general, we'll find that it's all pretty, this way, it should pretty much resonate, right? So, if you think about the experimental workflow for a sec, and we look at it at a very high level, maybe kind of an archetype, and sort of nowadays maybe in some cases it's cyclical or something, it's not linear, but all in general you have some element of something that triggers the reason to do an analysis. Maybe it's automated, maybe it's a specific request to do something. That in and of itself has a little bit of context around it. Why are you doing this? Then there's the planning aspect, the sample prep, submitting the samples to an instrument, controlling and acquiring data, really sort of at the core of the measurement. And then some level of processing, data reduction of some of the raw stuff, and then to get to a point where you can do an analysis of the data and find out what really happened, or what's the purity, or whatever it is that you happen to be looking at. And then there's a report out or provision of those results back to who or what process requested it. And then on a good day, that's stored and archived somewhere such that you can go back and reuse it and get more value out of it downstream, and use it in the context of a lot of other data. And one of the keys is that at each one of those steps, there's really critical metadata, critical context that's generated that at the end of the day is what allows us to make sense of, which button is this? This one. Make sense of these results down here, right? What were the methods? What was the approach? What was the reason? What was the therapeutic area? How is the instrument set up? If I do this on a different instrument, is the setup the same? And in fact, in some cases, if we were cleverer about it, we might be capturing things at the planning stage around the methodology, for example, that we want to run on the instrument. And maybe we could avoid having people look up something on their computer in the office in a PDF, print it, and then carrying that over to the lab to re-enter it into the instrument interface. The other interesting bit is that rarely is there one system that rules all, and in fact, we have a mix of different capabilities in the lab that support these individual unit steps. The result of that being that, for one, this kind of metadata that we want to accumulate and analyze and make sense of in the end is spread out across all of these different systems, different databases, different schema, different data models or information models. And so, to put together the complete picture along with that one particular result is enormously challenging. And of course, the other thing that this introduces, in as much as these are all different code bases, different manufacturers, different versions. So, there's a lot of challenge with respect to interoperability to wire these things together. It's anything but the kind of plug and play that we have on our phone, right? If you had to have an IT project every time you wanted to install a new app, I think Apple wouldn't exist anymore, right? And so that leads to what you might call knowledge mismanagement. And a lot of challenges in the lab. So, there's this manual transcription of the methods and the results. There's conversion of data from one format to another to get it into another system. On a good day, some of our workarounds might be as clever as taking the output in one CSV format, transforming it, and then uploading a different CSV into the downstream system. So this manual handling of data actually leads to a lot of opportunities for data integrity issues. Those kinds of workarounds, leave our infrastructure fairly fragile and brittle. So upgrades can be really painful. We break all these sort of clever little APIs and workarounds that we have. And at the end of the day, the knowledge about what these data really mean get accumulated in people's heads and on their desktop in Excel files, which might be great for them. Maybe they've gotten clever at managing their knowledge base via Excel, but it's not of much value to anybody else. And if you want to know, if you're getting results downstream and you want to understand what happened or what how the experiment was set up or why it was done, you don't necessarily have a nice system to go find it. You have to know who ran the experiment and then hope that they remember which folder that the results are in. So we get these silos of data, context, and meaning. And the outcome of this actually has some really major impacts on the core mission of our companies, which is to get medicines to patients. All of the manual aspect of this, all the document-based data flow, that adds significant delay in the pipeline at the end of the day. The data integrity issues have gone public, right, so to speak. When it makes the major newspapers and The Economist that there are challenges in data integrity, it significantly erodes the public confidence in the whole sort of scientific enterprise, right? Which is, core to what we do. And it wastes a lot of money in the irreproducibility. And in terms of our ability to move ahead to the next generation of big data, we have big aspirations for big data and artificial intelligence now. And in reality, anybody who's done a bit of data mining, for years has known that the rule of thumb is that it's 80% janitorial work, right? And a recent survey that Forbes republished that was done by Cloudflower of data scientists, and it just in 2016 verified that. So 60% of their effort, if you're a data scientist, goes into cleaning and organizing data, and that's after you spend 20% of your time looking for it. The value add are these little tiny slices up here. There's another interesting trend externally that sort of lines up with some of the principles that we want to head towards. Even though it's something that started in the public domain, particularly scientific literature, the principles of data being findable, accessible, interoperable, and reusable are, pretty much resonate, right? That's kind of universal. And if you delve into this paper and into this manifesto about, there's some core principles, and what we'll find is that what we're going to describe to you in the Allotrope Framework enable about 3/4 of those bullet points. And so it was this problem statement that led a number of us to stand back and say, wait a minute, let's rethink this. What are we trying to do here? So in executing science in the enterprise, right, it's not just the scientific method, but there's the core bit about making the observations, but sharing these results, either internally, externally, with regulators, that's a core need of being able to execute science at scale in the enterprise, and then being able to repeat it reproducibly. And if we got this right, or if we don't get it right, it impacts everything downstream from here. If we don't get it right, it has problematic. Our process execution is hindered. As I said, we have problems with data integrity and scientific reproducibility. It impedes our ability to leverage big data and do sort of more advanced analytics. But if we get this right, we can turn a lot of these things around. So if you stop and think, what we really need is a consistent way to record what we observe. And then we need a seamless way to share our findings with other people so they can leverage them. And then be able to reproduce that. If we got that right, given what we leverage in today's technology in our rest of our lives outside of work, we should be able to find any data we need in seconds, right? That should just be core to what we're able to do. We should be able to be 100% confident in the integrity of the data and then our ability to meet our quality and compliance expectations based on the results we're seeing before we make decisions. How many times do we sort of have to backtrack after an important decision and say, well, wait a minute, where did this come from? Is that right? And we should be able to really feed the next generation of analytics. So if we want to do AI, we need to feed the beast, right? That's data intensive. And ultimately get to a point where, as you'll see, we think we've got an approach where you could take a method, an analytical method, some kind of a measurement, and essentially build an executable version of it. What would that do for data reproducibility, right? If we get to the point where publications are not only getting data, but getting an executable version of the methodology that gets sent to an instrument. So those are our aspirations. To get there, there's a couple of root causes that we have to address. And they seem fundamentally very simple. They are simple, but doing them takes a lot of work and has been an interesting journey. The first is to move from the entropy of a data format for every different kind of instrument from every different kind of manufacturer. Of course, in some experimental platforms, we could generate 4 files for one measurement, to a place where we're working with one standard format for anything we measure. The second is to standardize our language, in effect, and the way we structure our language. Move away from the document-based and the unstructured approaches to the regulations, to the recipes, to our observations, to the methodologies, to a standard vocabulary and a standard structure of our metadata so that we can describe process, material, equipment result unambiguously. After a couple of years of research, proof of concept work, evaluation of a lot of standards, where we got to is this set of capabilities we refer to now as the Allotrope Framework, right? So at the core is a data format, the Allotrope data format. It's instrument, vendor, platform, technique, agnostic. It doesn't matter, right? You can put package any kind of data in it. And it's a format that's designed for high performance. It's binary. And within that, we've structured, actually, I think this is where I hand off to Wolfgang.
I'm enjoying your presentation.
No. I'll get us started on here, and we'll still use the transition. So that's really the core at it, right? A data format that is portable, reusable. We can use for a lot of different kinds of experiments. Wolfgang will get more into the details. Along with that, complementary to that, is the ontologies, right? The means to standardize and structure the vocabulary. And using those ontologies, we can describe the context, the metadata around our experiments, and insert that into the data format. And then further, and what's been really sort of an interesting learning in the last year or two is there's some new approaches on how to model the semantic expression of our metadata using a set of constraints and a new standard from the W3C. So those components together make up a quote-unquote framework, a holistic approach to standardizing, right? So even though there's a separation of concerns in terms of keeping the exact description and metadata outside of the data format in this reusable ontology concept, they work holistically together. And then finally, so that the use of these standards is unambiguous, it's not open to interpretation by developers every time somebody creates a new piece of software. Instead of just providing a paper specification, we actually provide the software components to work with this. And then finally, we will soon release essentially the equivalent of the free Adobe Acrobat Reader, the ADF Explorer, that will be able to read ADF files, and that'll be distributed for free. And so I'll hand off now to Wolfgang Kolsmann. Wolfgang is now he's the Chief Innovation Officer at Ostis, and Ostis, as you'll learn more about throughout the day, is really our key partner who's helped us design, architect, and build this framework. So here, I'll hold this.
Can you hear me? Is the audio good? So I'm excited to be here today. This is now exactly 4 years after we have kicked off the Allotrope effort in DC. So we met with 50 people from the pharma companies for a week to figure out what is it that we're trying to do here. The first year was research of existing partial solutions to the problem. Second year was feasibility study, proof of concept, piloting, and then followed by 2 years of framework development. And in June this year, we released the first product of the Allotrope Framework, the Allotrope Data Format, and it's exciting to see that over the next couple of weeks and months, we will have the first commercial vendor product on the market that implements this technology and puts this into practice. What is also exciting is to see how the community develops. So what started as a pre-competitive collaboration of leaders and scientists from the pharmaceutical companies has evolved to a pre-competitive collaboration of leaders and developers from our vendor partners. And all of these together provide a multitude of perspectives on the problem, but also on the solution. So we see this now in the Allotrope Connect meetings that go for 5 days now, that we have in one building a hackathon where developers meet, and the next room a strategic meeting of the leadership to figure out what the next 5 years will bring. And I think this is unique in this industry, that we have so many different skills together in one room. So then I was so kind to already introduce what the framework really is. And this is also part of this journey that we're making, so that the pharma companies and the representatives more and more understand the solution to the problem. And we also see that the presentations shift. So now pharma companies give more technical presentations than I do. And this is a good thing. So inside the ADF file, which is the first product that we have released, we have 3 major data types, if you will. The most basic data type is the data package. And this is something like a zip file, where you can package multiple raw data files, image files, reports, videos, audios, whatever you want to capture, share, and store long-term packages together. In addition to these files that we can transfer or store, we can store metadata that provide us with the context. So this sounds very simple, but it's key to the solution that we can find our data based on the contextual metadata. This is the missing piece that we often see. But even if we know in principle we should have this data somewhere, where do we exactly find it? And the metadata can be used, for example, to search for all data for a compound, for a project, created in one lab or in 1 year. So whatever the metadata is, can be leveraged to do so. But not only that, in this metadata layer, we also can capture more of the context. So what was the process that has been executed to generate this data? What material has been used? How was this material generated? How was it, or where was it procured? What are the characteristics of that? What is the specification? So all of this is part of the data description layer, where we capture the knowledge in the end about our experiment. The middle layer, the data cube, is a vendor-neutral representation and technology-agnostic representation of the measurements that we are doing, such as chromatogram or spectra, or any other time series data. So the real raw data, if you will, that underpins any results, conclusions, or decisions that we make in our scientific process. As one example of this metadata layer, how this is structured, in this case, it's an HPLC experiment, so we have information about the instrument, we have information about the material, about the process that was executed, and about the results of the data that has been generated. And if we put all of this together, then we have a holistic representation of the experiment, or in a more current language, we have a digital representation of our world, or the digital twin, as Gardner calls this. And this is key to go to a digital business and in the end to do all these predictive modeling activities that we want to do. So a digital representation is sort of the foundation of all of these new functions that we want to implement. Very simple example to give you an understanding how the data is described. So we're using semantic web standards, in this case ontologies, to describe the terminology that we use to describe our data. And in this simple example, we have an instrument ontology, and an instrument is comprised of several attributes and also may be decomposed into modules, and each module has attributes. So in this simple model, of course, if we grow this to small properties and more classes attached to it, we can have a holistic representation of a scientific process. In order to get to a realistic view, of course, we need to address different perspectives, or as we call them, lenses. So for example, a scientist will have interest only in a subset of these attributes. So he's interested, of course, in flow rates, because they are important for the experimental process. He's not so much interested about the serial number, right? So this is not really relevant for the outcome of the experiment. An asset manager, in turn, will have interest in the serial number, of course, because he's tagging and scanning things all day, but he's not interested in the flow rate. Flow rate maybe is a part of the specification of the instrument that you're buying, but this, right, is less important. And with all these different perspectives from the different working groups that we have within Allotrope that's trying to solve different use cases, then we get the complete picture of our ontology. And this is now, if we compile this all together, the model of an HPLC, so it gives you an idea of the multitude of properties that we capture. Very interesting discussion that we had this week, that we use as an example to guide us through the week, is what mobile phase is required for this experiment or for this method. So naively, we would say, okay, the response to this question is a simple label telling us the name of the mobile phase. If you want to do advanced data science, the label doesn't tell you anything. So we need to describe what that really means. So we need to decompose what a mobile phase is, and this is ingredients, materials, the process, how to prepare it, but also the specification. Right? So there's double-clicking on this question, we go into a graph, into its own ontology and form that we need to model in order to holistically capture this knowledge. This is a lot of engineering work because we need to make our knowledge explicit and teach the computer about our knowledge. And often we don't know what we know, so it requires a lot of discussion. discussion to clarify the words that we use to describe the problem or the solution to, in the end, build this into software. So the terminology then that we create in these working group discussions is modelized into several buckets, if you will. So the backbone is, now we go into the acronym world, the Allotrope Foundation Taxonomies, so AFT. This is a tree of terms that are connected by their essence, so what they really are in a taxonomical representation. I will talk to this in a minute. Based on this backbone vocabulary, we can then model these ontologies. Ontologies provide more relations between these concepts described in the taxonomy. And we have our backbone ontology that describes basic concepts like what is a material, what is a process, and how they're interrelated. And for this, we're using existing external standards to align to the outer world. So explicitly, we don't want to reinvent things that are already out there. Based on this core ontology, then we can create domain-specific ontologies. So, for example, a chromatography ontology, and we can further specialize this and differentiate between LC, GC, and SFC to provide additional attributes that are less universal than the one in the higher level domain. So this is just a subset of the ontologies that we have created, but gives you an idea what the concept is. This alignment to the basic formal ontology is very helpful to connect to other existing ontologies. So the OBO Foundry hosts, I don't know, I guess over 100 ontologies already that are all aligned to this basic metaphysical framework of the basic formal ontology. So this way we can really import a lot of already described concepts and reuse them in our world. The taxonomies inside are structured according to our scientific domains, and this is a snapshot from last year, but I think it's still on high level valid. So we describe materials, equipment, processes, results, and properties, and we have extended them by additional layers now. One important concept is the concept of a role that we've introduced this year. So the best example is to describe what is a sample. And what we learned is a sample is not a material. A sample is a material that is used in a context, and in this context, the material is a sample. If you think of an input sample or an output sample, again, this is a matter of context, because the output of one unit operation may be the input of the next unit operation. So these roles are a function of time, a function of context. And this is a concept that is provided by this basic formal ontology, which was very helpful to find a solution to describe these aspects on the data. Taxonomies, as I said, are just hierarchical structures, so they do not interrelate. Everybody has an idea about the taxonomy of plants or mammals. For example, I think these are the most prominent examples of that. And ontologies help now to interconnect different branches of the ontologies. So in this simple example, we would have a spatial region taxonomy, a plant taxonomy, and insect taxonomy, all very nicely structured. And then we can capture the knowledge that Florida has lemon trees, and lemon trees have a pest leaf mite. Right? So this would be a fact or some fact that we capture about this problem, which is specific to Florida. It's a silly example, but easy to understand. And this gives you an idea about the scale of the ontologies that we have modeled. So the color coding, again, reflects the different domains that we have. So currently we have roughly 4,000 terms in our ontology. 600 of them are related to LC. And LC will be the first example of these three products, data models, ontologies, and Allotrope data format that we will release this year and put into production with our vendor partners. So to put this all together, we have the ontologies, the data format, and the data models that inform the structure of our data that we capture. As the experiment flows through the process, we capture more and more metadata and get a richer and even more richer file. And in the end, then this file can contain all three layers of the information, and then can be used for reporting, search, reuse, modeling, whatever. Thank you.
Okay, so that's the basic introduction to the framework concept. There'll be a lot more opportunities to sort of get into that a little bit more, these different components, and a little bit more how they work together. But if you think about it, right, if we complete this process, if we're able to sort of structure our data, standardize its representation, get into a format that now is interoperable between different systems, is agnostic, you know, we can easily get data out of there with full context. Let's reflect back of what the impact of that kind of thing will be on our lives doing science. So first of all, you know, it gives us the opportunity to reduce manual effort in paper. So when you've got a standard vocabulary, you want to stand up a new application where you want people to create a method, you want people to capture stuff, you can drive all that now with drop-down lists or pick lists, right? You can just feed that vocabulary to the UI. When you can describe a method in a way that's literally reusable by an instrument so that you don't have to rewrite the thing, you just say, yes, we'll take that one, tweak a parameter and send it, that takes work out of the system as well and improves our scientific reproducibility, right? You take the interpretation out of going from document to instrument, and maybe the parameters weren't set up quite right the same way. By implementing those kinds of approaches that I just inferred on application design, you decrease the amount of work, freedom of expression at the keyboard, right? That's great if you're a literature major, you're writing novels or documentaries or something, but freedom of expression in the lab isn't a great thing, right? You want to get rid of that, and that'll improve the integrity of what goes in, and by making it easier to have richer context with the standardization, you get much higher quality data at the end of the day. If you think about how we might standardize our IT infrastructure, right? So on a good day, you've got an API with one system that can talk to an API with another, but then there's always a little bit of understanding the calls and that sort of thing. Well, what if we don't worry about that and we standardize on the representation of the data and the representation of the metadata? And if our applications and our systems started exchanging this data format, right? That's you know, n squared number of interactions between APIs to one interaction. When we can take that data that's described in this control vocabulary and put it in some kind of a repository, this type of an index that you can build on top of that, right, will literally make finding data in your enterprise like Google, right? When was the last time that you didn't have to go past the first page of your search to find the data you were looking for, right? How many times do you go past the first page on Google? Not very often. And then the ability to send, you know, give somebody else access to that, and for them to be able to, not only because, you know, they've got a system that can read it as well, but they can understand the context is there, that lowers the barrier for the sharing and data integration enormously. And as we said, with this richer, more consistent description and the ability to get access to this data, now we're in a position to actually do some real data science, right? To repurpose that 80% that's the janitorial work at this point. And then finally, from the standpoint of somebody who provides products or services to the pharma industry, this approach is essentially representing a consolidated set of requirements, right, from the customer base. I think it's hard to understand. You can be much clearer in your requirements than an API and an ontology, right? I mean, that's very specific. And then it also allows us to lower an innovation barrier. So not only is it in a more standardized environment easier to get new technologies in the environment, you don't have to make a decision, right? If you've got a new algorithm, new instrument, is sort of which sort of platforms do I aim to try and integrate with? But it also allows us to sort of move forward more quickly from our legacy. So, you know, how often do we delay an upgrade of a system because we still have data in a file format from 2 versions back that, you know, we lose backward compatibility with when we upgrade? So what we've got now is a path to move that legacy data into the data format, now the ADF, in a platform and a format that's actually going to grow into the future. So we've got now this, you know, an ability to sort of cut the ties to those legacy systems and bring the data along with us. So we've talked a little bit about the 3 components. We sort of chunked those out in terms of delivering those in a production-ready way into sort of three work streams. The first was to get a version of the Allotrope data format out of the ADF and the APIs this year, and we made that schedule. It was released 1st of July, basically. The second is a version of the Allotrope Ontologies defined with some fairly specific scope around particular use cases in HPLC, UV initially. That release is it's coming up soon. It'll be the end of this month, and based on the feedback we had this week and the earlier meetings we're at, which we did a lot of project management like stuff to really drill into this, you know, we're on target. So we'll meet our second deadline. And this third arm is the data models, or the data shape constraints that Wolfgang spoke to a little bit. There'll be a version of those out, again, you know, in the scope of the HPLC use case by the end of the year, and we seem to be tracking well on that as well. And then the ADF Explorer that I talked about is complete. We're going to do some testing and evaluation, sort of internal, just make sure it's all ready to go, and that'll be released into the public domain probably within a month or 2. So what we'll spend the rest of the day on is, you know, we're done with all this abstraction. The rest of the day is going to be talking about reducing the stuff to practice, right? Something much more tangible. And we've actually been, you know, within our member companies, working either independently or in many cases with our vendor partners, implementing solutions that integrate some aspect or sometimes many aspects of the framework, which has really helped us accelerate the development because we've essentially given back, right? We've done some extensions to some of these things and given back to the foundation. It's been a great way to, you know, accelerate the adoption with our vendor partners. There's nothing like doing to learn, right? And so, you know, by creating these projects, there's opportunities to work together to figure out how to actually implement these kinds of things. It's given us the ability to road test things. And amongst one another, I think we've had an enormous number of learnings about not only how to implement these standards in the variety of systems and environments and architectures that we have in-house now, but I think more generally about, you know, how to do lab informatics better. Which is a great benefit of being part of this collaboration. And finally, you know, it's really helped us as we start to implement, we start to understand what this is going to take, we understand how we start to impact things, we understand how to now build this into our IT strategy so that we really are planning the future based on this kind of thing in our architecture as opposed to just reacting to it. So again, the rest of the day, there'll be a series of presentations in 2 chunks from some members, some from our vendors. Take the time to learn more about those. There's also many more presentations in the poster session. I want to wrap up on a couple of things. One really important concept to keep in mind is, you know, the data format itself, as we said, is really agnostic to any kind of techniques or workflows. And whilst we are going to focus a bit, in some cases, on what we're doing for HPLC, UV, the beauty of this architecture, this approach, is that our extensibility into new techniques, new domains, new applications really just requires extending these ontologies and data models, right? So it doesn't break anything here. It's external to that data format. And sort of operationally, the way we do that is by getting together and collaborating in working groups around different sort of technique or workflow areas. And I've just got a few of them listed here, but besides the HPLC UV, we've got working groups up and going for mass spec and NMR. We're starting to kick up some dust around flow cytometry now. And you can see that these are, you know, attended by and draw from contributions across both the member companies and the vendor space. And, you know, in these places, people are coming to agreement on what to call things, right? So when we can harmonize terms, because everybody recognizes, well, this doesn't need to be a special word for my system, we can use a common word, we do that. And every now and then you discover that there are some unique parameters, and that vocabulary goes in there as well. We've also used this working group concept to get a lot of other operational things done in the foundation, and so even in those respects, we've got the APM members collaborating with us in that space. So there's really, you know, increasingly a joint ownership of this collaboration. And of course, you know, we have to manage this at some point, at some level, so it doesn't become completely chaotic. So, you know, if you want to know more about how we've organized and, you know, what's going on both in terms of the operational stuff and product delivery stuff, you know, catch one of us on the break. And this is the current community at this point. I just had to update this morning, which is a great problem to have. You know, just in the last couple of weeks, we've added a few new partners. So the Allotrope Foundation members, you know, coming from the biopharma space are listed here. So you got kind of a mix of large molecule, small molecule, people who do both, a little bit of geographic distribution. As I mentioned, Ostis is our key technical partner that's provided the architecture and development resource for this framework. You met Jamie. There's many other people here from Drinkle, Biddle, and Reith, a firm that provides our project management, our collaboration support, our consortium management, and, you know, frankly, it's kind of our back office. And, you know, one of the important decisions I think we made early on in this endeavor is that, we weren't going to try and develop the technology, you know, with a bunch of people sort of 5% of their time here and there, right? We recognized that when we got this going in 2013, we needed to deliver things of value in like the 3-year time frame before people lost interest, frankly, and moved on. And we wanted the expertise. We wanted dedicated experts, and we wanted people who bring a perspective outside of our industry, and we get that with Ostis. The other is that we also recognize that, you know, as much as we try, you know, scientists and folks in IT don't always make the best project managers or, you know, facilitators for a consortium, and it's time consuming. So we also didn't kick off until we had sort of enough critical mass to fund these guys to help us with that, as well as Ostis. And this is the ever-growing Allotrope Partner Network, the vendors of instruments, of software, service providers, integrators that have joined the network and that are at various stages of building their expertise in this adoption. As Janet said, we know that on the near horizon, actually, there's a number of people that have this in their product portfolio now, support for the framework. So you're certainly customers of one or many of these people. Go talk to them today, find out what they're up to, what their plans are, enjoy the talks, and look at some of the posters. Finally, and I mentioned a little bit, so there's benefits about adopting the technology, but there's benefits just inherent to being part of the foundation. So, you know, one of the core things, actually, obviously, is that if you're part of it, you can help influence the direction and speed at which we move. We're at a juncture now that we've established the sort of base technology to start making some decisions about what are our next techniques, where do we invest first, right, or the next. Be part of this community of experts that's expanding, and I tell you, for a lot of us in the industry, this has been one of the best places for us to learn and get tooled up on semantics, right, which is driving a lot of technology, but it's not something we have, I think, deep experience yet in our industry. Obviously, you have access to support and training through the foundation. well, you know, we can talk more about it in the networking session, but there's things that we do as part of our work in enabling ourselves with the framework that generates things that we give back to the foundation. So there's some benefit of shared investment here. You could, in sense, in principle, not be a member of the foundation and buy technology that's enabled by it soon, right? But you can't buy competency, right? And you can't buy the understanding that allows you to really build these kinds of capabilities, this kind of a data strategy, you know, into your vision, into your IT strategy. And that really comes as being part of this. And finally, if you think this is the right thing to do, right, if this is going to be useful and you think that we're right about at least some of the value proposition, then we have a responsibility to sustain this, right? It's a matter of corporate responsibility of our industry because of the impact ultimately it does have on patients and data integrity. We were pleased this year to be recognized, right, with the BioIT Best Practice Award, and so for the non-IT people in the world, this is a great little nod from the geek community. BioIT is probably the biggest, most significant meeting for IT, at least in the R&D world. So we were recognized for the advances here in knowledge management. So that was really exciting and part of a big year with the releases and this as well.